To build a modern mobile device, you don't start in one place. You start by aggregating roughly 400 distinct components manufactured across 43 different countries. The most complex of these elements is the processor. The hyper-pure silicon that powers the device is fabricated exclusively in advanced semiconductor facilities in Taiwan, an intensive process that takes nearly 3 months to complete. At the exact same time, OLED displays in ultra-clean rooms in South Korea, and high-resolution camera sensors are being polished to nanometer tolerances in Japan. The core logistical challenge of modern electronics is taking all these highly sensitive parts, sourced from opposite ends of the Earth, and mathematically synchronizing their arrival at a single physical integration point. That convergence happens here, in Henan Province, China, at a massive manufacturing campus often referred to as iPhone City. The scale of this infrastructure is difficult to conceptualize. It is a 3-square-kilometer enclosed campus that houses over 200,000 workers, operating 24 hours a day, 7 days a week. Inside, dozens of parallel production lines break the massive job of assembly down into highly specific, repeatable tasks. What happens on those lines is a rigid 10-step sequential process. Every single movement is governed by extreme spatial constraints and microscopic tolerances within this bare metal frame. Pushing millions of units through this gauntlet requires a strict marriage of human manual dexterity and automated machine vision metrology to ruthlessly eliminate physical variance. This diagram illustrates Step 1, frame preparation. Automated metrology machines scan the bare CNC machined frame to verify every cut meets structural tolerances. The metal is then swept with an ionized air bath to remove microscopic dust particles. Step 2 introduces the logic board. This central circuit board containing the processor is seated into a precision fixture directly inside the frame. Robotic arms take over to secure it in place, driving 0.9 mm titanium screws through the board and into the metal chassis. The driving torque is strictly governed in millinewton meters. The screws must be tight enough to survive an impact, but if they are over-torqued by even a fraction, they will fracture the brittle silicon components. This foundation has to be mechanically perfect. The spatial alignment of every module added downstream depends entirely on the exact positioning of this first layer. For Step 3, a flat lithium-ion pouch cell is physically inserted into the lower section of the frame. The battery links back to the main logic board using a zero insertion force, or ZIF, connector. Beneath the battery goes a small adhesive pull tab. This allows the battery to be cleanly removed later without puncturing the volatile lithium-ion pouch, ensuring the device remains repairable. Step 4 fills the remaining lower cavity. The Taptic engine, a linear actuator for haptic feedback, and the bottom audio drivers are mounted into their respective brackets. After these modules are placed, overhead machine vision cameras automatically photograph the subassembly to verify that every tiny ribbon connector is fully and perfectly seated. Human hands maneuver the delicate modules into tight spaces, and automated optical systems verify the structural perfection of their work. Step 5 introduces the camera module, seating a highly complex multi-lens stack directly into the rear housing. The spatial constraints here are absolute. Even a fraction of a millimeter of misalignment will severely degrade optical image stabilization and zoom performance.
Step 6 installs the biometric infrared module into the top of the frame. This is where assembly becomes digital. On the physical production line, this biometric hardware is cryptographically paired and permanently locked to the logic board's secure enclave processor. If you swap a Face ID camera outside of an authorized facility, the feature immediately breaks. The hardware and the software are now mathematically linked. By this stage, physical assembly and cryptographic security have merged, permanently bonding the hardware modules to the device's internal brain. Step 7 seals the front. A precision jig is used to lower the delicate OLED panel directly over the completed internal chassis, perfectly aligning the outer edges. An industrial adhesive bead is applied around the entire perimeter, and the device moves through a station where UV light or heat precisely cures the bond. Step 8 creates the water resistance. Silicon gaskets are compressed around every external opening, including the charging port, speaker grills, and physical buttons. Achieving the exact compression on these gaskets guarantees the IP68 rating,
allowing the device to survive submersion in 6 meters of water for 30 minutes. Step 9 applies the back glass. Exact alignment tolerances are required here to embed the circular magnetic charging ring flush against the rear panel. For step 10, the final external structural screws are driven into the base, physically locking the entire enclosure together. The completed unit rolls into a final automated visual inspection chamber. Camera arrays photograph the sealed device from every angle, searching the surface for microscopic cosmetic defects. At this stage, the device is physically sealed. It contains roughly 16 billion transistors wrapped in a flawless mechanical enclosure, but functionally it is entirely inert. Hardware assembly is only half the process. The assembled device remains unresponsive until it is moved to high-speed programming stations. First, a factory build of the operating system is flashed onto the memory. Unique hardware identifiers, like the logic board's serial number and Wi-Fi MAC addresses, are permanently written into Apple's global product database. Next comes individual display calibration. A colorimeter measures the specific light output of the OLED panel and generates exact correction values, so the screen perfectly matches a wide color gamut standard. Biometric calibration follows. The front-facing projector fires 30,000 infrared dots against a physical reference surface to perfectly map and verify the depth sensor's alignment. Finally, the device enters a shielded test enclosure. The battery is cycled, the 5G antennas are checked for signal integrity, and the gyroscopes and accelerometers are verified. Every individual sensor on every phone leaves the factory mathematically tuned to a universal performance standard. To maintain this standard, a percentage of devices are pulled off the line and deliberately destroyed. These units are subjected to aggressive drop tests and intense thermal cycling processes to verify their complete internal structural integrity. This critical data graphic reveals the ultimate metric of success for this entire global operation, the final defect escape rate. Achieving a near-zero defect rate while pushing millions of individual units through thousands of human hands and automated touchpoints requires immense industrial discipline. High-volume manufacturing at this scale relies on eliminating physical and digital variants at a microscopic level. This finished final product represents the culmination of the world's most synchronized industrial ecosystem, rendered in glass, metal, and silicon.